Another exactly soluble Hamiltonian in quantum mechanics is that of the free particle. We're going to start with the free particle wave function that we can solve easily. And then we're going to look at the properties of the free particle, realize that wave packets are the real free particles and their properties, and then talk about phase and group velocities. So the free particle wave function, it seems that this would be a very simple case. However, in quantum mechanics, this is actually complicated and needs to be treated really carefully. And we'll have a whole segment on how do you do normalization and orthogonality for this particular kind of function. So let's start by realizing that in a free particle, in principle, the Hamiltonian has v equals 0 everywhere. That means that the Schrödinger equation becomes really simple. Minus h bar squared over 2m d squared psi dx squared is equal to e times psi. If we just rearrange it in the normal way, we get d squared psi dx squared is equal to minus 2m over h bar squared e times psi. And this we'll rewrite as minus k squared psi, this being k squared. This is exactly how we did it with the particle in an infinite square well. Now, before we chose the sines and cosines, but from the Euler relation, we know that that's equivalent to choosing complex exponentials, e to the plus I omega t and e to the minus I omega t, or kx, whichever. And so, in this case, we want to choose the exponential forms. We could choose the sines and cosines, but the exponential forms are better for a free particle for reasons that we'll see in a minute. So we're going to choose psi of x is equal to a e to the ikx plus b e to the minus ikx. So these are complex exponentials with a change in sign, but they're both just complex exponentials. If we add back the time-dependent portion, and we call it e to the I, e to the minus I, e over h bar t, and we'll call e over h bar omega. So we have e to the minus I omega t. The full function then becomes psi of x and t is equal to a e to the I kx minus omega t plus b e to the minus I kx plus omega t. Well, if you recall your wave mechanics from very general physics, you realize that these are simply traveling waves. They go in the positive x direction, this one, and the negative x direction, this one. And so we can rewrite this a little bit differently. We're going to say this is equivalent to writing the solution as a e to the I kx minus omega t, where k is positive or negative. So k is related to the momentum. It's a wave number that's related to the momentum, and it can either be positive or negative. So they have square root of 2 me over h bar, that's a positive definite quantity, and then k can be either positive or negative of that, because you're taking the square root. So our solution then looks like this. Psi of x and t is a e to the I kx minus omega t, where k is equal to plus or minus square root of 2 me over h bar. The wavelength of this particle is just 2 pi over the absolute value of k. The momentum of the particle, according to the de Broglie relation, is just h bar k. P is equal to h bar k. The speed of the traveling waves, described by this wave function, is given by omega over k. That's the dispersion relation, and that says v quantum mechanical is omega over k because of these two relations. Because the momentum is also mv. And so you can get that. So in this particular case then, omega is related to the energy, and the energy is related to k squared. So we have h bar k squared over 2m times 1 over the magnitude of k. If we then rewrite this, the magnitude here cancels the absolute value of the k on the top. And so you have h bar k, absolute value of k over 2m is the velocity. And then if we put in what the value of k is, we have h bar over 2m times the square root of 2me over h bar. And finally, it's just square root of e over 2m. So that is the velocity of this traveling wave. Now, if you think about this, this is just the half of the classical speed coming from a kinetic energy of 1/2 mv squared, because this is using the de Broglie relation instead of this relationship here. So for kinetic energy in a classical system, you have that v is equal to 2e over m square root. But this is just twice the value of the quantum mechanical. So we have two different values for the velocity. The wave that solves the Schrödinger equation moves twice as fast as the particle would actually move in a classical sense. And this is a problem because by what's the so-called correspondence principle, if we start with a quantum mechanical particle and we take it to the correspondence limit of classical physics, we should get a classical result. And this is not the classical result. Now there's another problem with that, with this wave function. And that wave function is that the wave function cannot be normalized because this amplitude is constant everywhere in space, right? No matter where you are, you'll get an oscillatory function. And so when you square it, it's always going to be positive, and it never will get bigger than a, but it'll never go to 0 at infinity. And so when you integrate it, it'll give you an infinity. And so this is a problem. The function does not trend to 0 at plus or minus infinity. So this is why the free particle, although it seems very simple to solve, is a very complicated and delicate thing to deal with. So what does this say? It says that a state with definite energy, a specific value of k, specific value of omega, is just not a valid state for a free particle. Not only can it not be normalized, but it also doesn't have the right kind of velocity. So what is the real free particle? Well, even though the stationary states are not possible wave functions because they can't be normalized, they can be used to construct a valid free particle wave function. And that's called a wave packet. And a wave packet has is a sum of free particle stationary states with a momentum distribution, or an integral of them, actually. The other thing is this is the continuous variables, right? So psi of x and t then would be 1 over the square root of 2 pi integral from minus infinity to infinity of phi of k e to the I k minus omega t dk. So when we integrate the k out with this distribution, we'll get a wave packet, a function that is a superposition of a bunch of different values of k, depending on what this function is. Now, if you look at that, you should be able to say, that looks like a Fourier transform. And in fact, it is a Fourier transform. So phi of k is simply the Fourier transform of the wave packet, or the wave function that you really want for the real particle at time equals 0. And so phi of k is simply 1 over the square root of 2 pi minus infinity to infinity, integral of minus infinity to infinity of psi of x and 0 e to the minus I kx dx. So this is a Fourier transform of the time equals 0 wave function. The time-dependent wave function, which has the time built in here, is a superposition that has the momentum distribution given by the Fourier transform of the time equals 0 wave packet. Now what that means is that in principle, over time, this will change. This distribution will change. It won't be the same at time equals 0 as it is at time equals t, and we'll see how that works in a little bit. But it's very clear that that will be different because every one of these waveforms has a different velocity. Right? K is different, the velocity is different. So if we recall the relationship between Fourier transforms, we have the Fourier transform here is the Fourier transform of f of k is equal to f of x e to the minus I kx dx, integrated from minus infinity to infinity with the 1 over square root of 2 pi. And the inverse Fourier transform is just f of x is equal to 1 over the square root of 2 pi, integral from minus infinity to infinity, f of k, capital F of k, e to the I kx dk. So you can see how these two functions are sort of related as Fourier transforms. Now, if you remember, we computed two different velocities. How does that work now that we have a wave packet, that we made a superposition of a bunch of different functions? Well, the quantum velocity we figured out for a single stationary state was VQM is equal to the square root of E over 2m. And the classical velocity was square root of 2e over m. And this discrepancy was a problem. So it's 2 times VQM. Now, the wave packet's a superposition of sinusoidal functions with amplitude modulated by phi of k. And so a wave packet looks like this, like a high frequency oscillation modulated by an envelope, right? So you have a high frequency oscillation, which is the superposition, and the envelope, which is the phi of k, which gives you the envelope in space. The quantum velocity is the phase velocity, that is the velocity of the individual component. And the classical velocity is the group velocity. That's the velocity at which the envelope moves. And we'll see how that works in just a little bit. So this relationship between the group and phase velocities depends on the physical system and is related to the dispersion relation, which is the expression omega as a function of k. That is, the angular frequency as a function of the wave number of the wave packet. So let's see what the velocity of a free particle wave packet would be. And we'll start with the definition of a wave packet. A wave packet is given by 1 over square root of 2 pi, integral from minus infinity to infinity, phi of k e to the I kx minus omega t dk. If we assume that phi of k is a narrow distribution around some central value k sub 0. If it's a narrow distribution, only the values of k approximately equal to k0 contribute to the integral. So we can simplify the integral. And so we can then approximate omega of k with the first two terms of its Taylor expansion. So omega of k is equal to omega sub 0, which is the central value, plus omega prime, this first derivative with respect to k of omega, times k minus k sub 0. We'll now change variables from k minus k sub 0 to s. And so we have k is equal to k sub 0 plus s, and dk is equal to ds. So we take this integral, replace this for omega of k, we replace this for k, and we get an integral. So we place these two, the blue stuff goes into omega, the red stuff goes into k, and the s goes in for dk, and we get the following integral that we do. So omega of x and t is equal to 1 over the square root of 2 pi, integral from minus infinity to infinity of phi of k sub 0 plus s, that's because we made this substitution, e to the I k sub 0 plus s times x, minus omega 0 plus omega prime sub 0, omega 0 prime sub 0 times s times t, integrated over ds. So this is the integral that we want to do. At t equals 0, right? So if we set t equals 0, this is exactly this value. So omega of x and 0 is equal to 1 over the square root of 2 pi, integral from minus infinity to infinity of phi of k sub 0 plus s, e to the I k sub 0 plus s x ds. And at time t, we can rewrite this in the following way. And we'll take a look at what we've done. I've taken this term here, I put it down here. And then I've multiplied by two terms, e to the minus I k0 omega prime sub 0 t, and e to the plus I k0 omega prime 0 of t, and integrated by ds. So basically, I'm adding and subtracting these exponents, which shouldn't change anything. But now, I can pull this one out, but now I have this one. This altogether now can be simplified, because I can regroup this, and I see that I get this in the following way. So the first thing I'll do is I'll take out all the terms that don't have anything to do with s, because in an integral I'm integrating over s. And I can get rid of this term here, I can get rid of this term here, and this term here. They only depend on time, they don't depend on s. So that gives me 1 over square root of 2 pi e to the I minus omega naught t plus k sub 0 omega sub 0 prime times t. And then what's left in this can be recast. So this term comes out, and then I'm going to take the term out that has the omega sub 0 times t. But I'm going to leave everything else in, because now I can rewrite this as k sub 0 times omega prime 0 plus s times omega prime 0 times t. Right. And so I get phi of k sub 0 plus s. And now I've changed the variable up here to e to the I k sub 0 plus s times x minus omega prime sub 0 t ds. Right? So I have the two terms that are in terms of this variable here, k sub 0 plus s instead. But now notice what I've done is I've changed from x, which I had before, to x minus omega prime sub 0 t. So this equation at time t is identical to the one at time equals 0. So if you look at this and compare this one and this one, it's identical to that, except with a phase shift, and the phase shift is here. These all just depend on time, and with x here replaced by x minus omega prime sub 0 t. But that is really, then that means I can write it like this. Psi of x and t, which is up here, is this, is equal to the phase factor, e to the minus I omega naught minus k sub 0 omega prime naught times t, times the wave function at x minus omega naught, omega prime 0 t, and time equals 0. What this means, that in a time t, the wave packet has moved a distance omega prime sub 0 t. It's just moved over. Because this is the equation, this is the wave at time equals 0, but shifted by this amount with a phase factor. So what this means is that the velocity of this wave packet is related to omega prime sub 0. So Vg is omega prime sub 0. But that's equal to the derivative of omega with respect to k, because that's the first Taylor series expansion term, evaluated at k sub 0. So now we can look at the group velocity as d omega dk as a function evaluated at k sub 0. And the velocity of the individual wave function components is omega divided by k. So each of the components has its own velocity, but the group as a whole moves with a velocity that is the derivative of omega with respect to k, evaluated at the central value of k. So the relation between the frequency and the wave number, that is the dispersion relation, looks like this. Omega is equal to h bar k squared over 2m. When I take the derivative of omega with respect to k, I get h bar k sub 0 over m. Right? Take the derivative, I get the 2's cancel, and I get a k here. And I evaluate at k sub 0, I get k sub 0 over m. And the other velocity evaluated at k equals 0 is just omega divided by k. And that's h bar k over 2m. And so you can see that this relation of a factor of 2, where this is 2 times larger than this, makes perfect sense. And with the wave packet, we've resolved this correspondence principle, because the real function, the real kind of wave function for a free particle, which is a wave packet and not one of the stationary states, has the right classical velocity. So the group velocity is twice the velocity of the phase velocity of the central component of the distribution. And everything works just fine. And we will look at simulation next. So there's a program that allows you, that's written in Python, that allows you to do a visualization. And this is what this program plots when you run it in Python. So you have the probability distribution, which has this black line. And then you have the real and the imaginary components, because of course this is a complex exponential, so it has real and imaginary components. They're both sinusoids. And they're the real is blue and the imaginary is red. So if we start this wave packet looking like this at the beginning, so at t equals 0, this is the wave packet. And it's a superposition of a bunch of the stationary states, that is the traveling waves. At a time later, you notice that it spreads and its intensity and its amplitude goes down. At a time even further later, it's spread even more. So the function starts narrow, but over time, as it moves, it spreads out. And the reason it spreads out is because each of the components that makes up the wave packet travels at a different velocity. Some go slower, some go faster. The central one, of course, moves at its particular velocity. You can find this program at the SciPy cookbook. It's called Schrödinger FDTD.html. You can download it, you can run it, and you can play with it yourselves and see, get a good feeling for the